Hi, Year 12 Extension 1 students. Sorry for making you wait so long for some content, but it's been pretty crazy in the first week of this basically school shutdown. As a maths department, we've had to really learn a lot of skills fast to try and work out how we're going to deliver video lessons to you guys. I've been driving all around Sydney. I drove up to Manly to get some special cameras we could use for the department. I spent the first 3 days of last week from the shutdown. So basically, well, even Tuesday, Wednesday, Thursday, Friday, I would say, training staff, buying equipment, and as a faculty, figuring out how we're going to deliver content. So now we've got all that sorted. You should be getting regular content from me from now on for Extension 1 and also for the Extension 2 boys as well. Now, it does take longer to prepare lessons using online learning, but let's see how we go. We're going to look at solving dy dx equals f of x times g of y. Now, I should say that most of you are here for this lesson, but there were some people missing. This lesson is for those people who are missing, but it's also for the people who are here on that day because I've just added some extra detail to the notes. So that will help you understand the concepts better and also help you answer questions better. So even if you are here for the lesson on this, please make sure you download the notes, print the notes out, and then write down everything that I do on the screen. Okay, so let's have a look. Now, first of all, a direction field. A direction field and a slope field mean the same thing. So that's something to be aware of in terms of language. Now let's have a look at our first question. We've got to find the slope field or direction field for the differential equation dy dx equals 3x squared y. Now the method is in 2 steps mainly. So step 1 is you determine slope values along vertical lines through substitution. That means you're substituting x and y values into your differential equation here. Okay, so you're just substituting x and y values. Now, which x and y values do you put in? Well, basically, you put in x and y values which correspond to individual points. So, for example, you could put in x equals 1, y equals 1 because that corresponds to an individual point. Or you could substitute in particular x and y values, depending on the case. So particular x and y values. So typically, if you're going to sub in individual values, then you'd be looking at subbing in x equals 0 and y equals 0. I'm using a virtual pen here, so I'm doing my best to learn how to use this virtual pen. So if I draw in the wrong spot, sometimes it's a new tool for me. Okay, so basically, just to summarize, here's your differential equation. You're going to be finding different values of dy dx for particular points on your number plane. Now, those points you're going to choose will lie on a vertical line. Now, just something to be aware of as well is down here. Here we go. Down here. Look for any symmetries for dy dx values or any patterns. That can sometimes save you time in sketching. So let's see how this works in reality. Let's start with just writing down the differential equation here. So the differential equation here is dy dx equals 3x squared y. Now, I would also, just for the sake of abbreviation, write this down as y dash equals 3x squared y. So I'll be looking at that. Okay. Now, first things first, we're going to look at some points. I would start off by saying, let's look at the obvious ones. So, if x equals 0, y dash equals 0. Okay. And if y equals 0, y dash equals 0. So the first thing to do would then be to go to your number plane and sketch what we've done there. So at y equals 0, the derivative is 0. So that means all along the x-axis, derivative is 0. But also when x equals 0, the derivative is 0. So you're going to sketch horizontal lines all along the y-axis here. Okay, that's that part done. Now, what else do we have? Well, something else we're going to look at is we're going to look at all the points along the vertical line x equals 1. Okay, so to do this, let's have a look. Let's change pen colour. Okay, how about green will do. All right, so what can I say at x equals 1? Well, I can say that if I substitute that into dy dx, what do I get? I get 3 times 1 squared times y, which is just 3y. Okay, so what I would do is table of values. Okay, now I'm looking at all the points along x equals 1. So I'm actually just want to know what the y values are and what the derivative values are. Okay, so I'm just going to go from -2 to -1, 0, 1, and 2. Okay, so if we sub in y equals -2 into our derivative, dy dx equals 3y, you're going to get -6. And if you sub in -1 into 3y, you're going to get -3y. And if you put in y equals 0 into that, you're going to get 0, as we know. And if you put y equals 1 into dy dx, you're going to get 3, and then obviously 6. So if we were to sketch that on the number plane, let's have a look at x equals 1, right? And y equals -2. The derivative is -6. So if I went to 1, -2, I'd get -6 for the gradient. And if I went to x equals 1 and y equals -1, the gradient would be -3. Then x equals 0. Sorry, y equals 0 and x equals 1, the gradient would be 0. So you can see the gradient is negative and it's getting flatter. Then after 0, you can see the gradient is getting steeper. So let's have a look at x equals 1. Okay, we've got a 0 gradient, yes. And at x equals x equals 1, y equals -2, the gradient is -6. So if we go to, let me just change colours here. So, here we go. All right, so at this point here, right, I'm going to just draw a little negative gradient in there, and the gradient will be -6. Now you just got to estimate this. So let's just say this is fairly steep. There we go. There's a little gradient. We'll call that -6. Then at x equals 1 and y equals -1, the gradient is -3. So I go to 1, -1, and I've got to draw a gradient which is negative but not as steep. So maybe something like that. And then I get to x equals 1 and y equals 0, and obviously the gradient is 0. Then at x equals 1, y equals 1, the gradient is 3. Okay, so it should be like so. And then at x equals 2, at x equals 2, at x equals 1, y equals 2, the gradient is +6, so that's going to be a bit steeper again. Okay, now essentially you can see gradients are getting steeper. Gradients are getting steeper as we go, so you can do it like that. Now, the other thing is, if at y equals 1, you can look at this in terms of horizontal gradients as well. At y equals 1, now we've got to look at the, I'll just take that back. The next vertical line we're going to look at is x equals 2. Okay, so x equals 2. All right, so at x equals 2, what can I say? dy dx is equal to, now don't forget your differential equation. What is it? It's y dash equals 3x squared y. So if I put x equals 2 into there, what am I going to get? I'm going to get 12y. Okay, so table of values. And we're going to do y and y dashed. Okay, I'm just going to go from -2. You can do y if you wanted. Once you see the pattern, you can see what to do. -1. We've kind of already done 0 anyway, haven't we? Do it anyway. 1, 2. Okay. Now, let's see what's happening. If I put y equals -2 into this, I get -24. And if I put y equals -1 into that equation, I get -12. If I put y equals 0 into this equation, I get 0. And then I get 12 and 24. That's 12 there. Oops, missed that one. Click on the eraser. Right. Oops, the daisy. Okay, now let's draw that line back there. 12 was in there. Okay. All right, so at x equals 2, you got x equals 2. What's happening? I can see that the gradients are getting steeper, right? And they're steeper than before. So if we just change colours back to red, all right. So they're steeper than before. So in fact, they're quite steep. So at x equals 2, and y equals 1. I'll do the positive ones first. X equals 2, y equals 1. Okay, that's a gradient of 12. Okay, should be steeper than the previous one. And at x equals 2, y equals 2, gradient is 24, really steep. So you can see that's just going to be getting really steep. Now do the negative values at, and then obviously we've got 0 here. And at x equals 2, y equals -1, the slope is -12. So that should be something like that, steeper than the one at x equals 1. And then at x equals 2, y equals -2, you've got a slope of -24, so that's really steep. So you can see that's just getting steeper and steeper. Now, we can save ourselves a little bit of time here because we should notice that there is some symmetry occurring. All right, now, where's this symmetry occurring? Let's have a look. Let's try pink. All right, so the symmetry will occur because at x equals -1, right, what can I say about y dash? Y dash will be 3y, okay, which means all the slope values along the vertical line x equals -1 will be the same as these guys. Okay. What else can we say? At x equals -2, right? Y dash equals, we'll put -2 into your 3x squared y. What do you get? You get 12y. And that is the same as down here. You can see here the dy dx equals 12y. Rightio. So that means we can use the same table of values for x equals -1 and the same table of values for x equals -2. So let's have a look at x equals -1, right? Now, at x equals -1, these values here will be mirrored, won't they? So -1, -2, the slope is -6. All right, so you can think of just looking at the line x equals 1 and just mirror the slopes that you've drawn. So there, it's getting steeper, 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 steeper. And here, mirror image. Okay, it should be the same as getting steeper as you go along. All right, and at x equals -2, it'll be the same line as x equals 2, or the same slope as x equals 2. So you're going to have, don't forget your 0 there, 0 there. And these guys will be steeper, so that should be steeper than at x equals 1. And getting steeper again. And then this is really steep again, and getting steeper. Let me just move that hand out of the way. There we go. And getting steep, just keep getting steeper. So you can see that it's going to take ages to draw as a slope field. The main thing is that you understand how the slopes are generated, not necessarily how to draw the whole slope field for the whole number plane. It's going to take ages. You're more likely to get slope fields or have to complete the rest of the slope field, but to draw an entire slope field in an exam, that'll be a waste of time. Okay, so let's now have a look at this. So this is your slope field completed. And what we're going to do is we're going to sketch a possible function that would have this as a slope field. So a couple of things we can do when we're thinking about this. We've got to remember that dy dx, first of all, that's where everything is coming from, 3x squared y. Now, let's think about this in terms of limits. As x approaches 0, what's happening to y dash? That's approaching 0 as well. And let's just have a look at down here. Try not to write on an angle. Here we go. And as y approaches 0, what happens to y dashed? It also approaches 0. Okay. Whoops. I just want the pen tool back. There we go. Also approaches 0. Now the other thing to consider is what happens when y is bigger than 0. If y is bigger than 0, then I can say y dashed, the gradient is positive. And if y is less than 0, I can say that y dash will be less than 0, won't it? So if you look at let me just change the color here. So look at your derivative. Oops, not there. If you look at your derivative here, all right, if you substitute, if you look what happens as x approaches 0. As x approaches 0, this gradient will approach 0, won't it? And if y approaches 0, the same thing, dy dx approaches 0. The other thing to consider is if the y values are positive for this differential equation, that means dy dx will be positive. And if the y values are negative, that means dy dx will be negative. Okay? So that's something to consider when we're doing this. So we're going to have to look at two cases then, aren't we? Case 1 will be this one. What happens above the x-axis? Okay, so let's see if we can sketch that. So I'm just going to get the eraser and rub out that green bit there. And let's go back to a different colour, maybe blue. All right, so let's say pick a point, I don't know, anywhere along, let's start somewhere along the y-axis here. Okay, so at x equals 3, right, that's the slope is 0. And then at x equals 1, we'll do x equals 1 next. X equals 1, I'll be looking at a slope like that. So you can sort of see how it's coming along. X equals 2, that's really steep up here somewhere. X equals -1, let's use that dash there. So x equals -2, that dash there, x equals -3. It's getting quite steep. And well, we've got to approach 0. Think about it. As y approaches, look at this, as y approaches 0, right, the slope is approaching 0. So we could think of now sketching this, horizontal there, steep there, and then I'm flattening out and I'm approaching 0. Okay? Approaching 0. Now, what about below the x-axis? So we've done this part now already, that's y bigger than 0. Now what about y less than 0? Well, let's pick the mirror point sentence. So, okay, y equals -3 and x equals 0, slope is 0, no problem there. And there should be a symmetry about this. Let's see if you can see why. So that's at x equals 0, go to x equals 1, and then that's getting steeper. And then at x equals -1, put this in here like that, getting steeper, steeper. But don't forget, as I'm approaching y equals 0, I'm going to have to flatten out. So 0 and approaching 0. So you can see here that I should have two basically horizontal parts of the curve, or curve where the curve is getting horizontal. And that's just there, and also just here, that should be approaching 0 as well. So you can see there's a bit of symmetry about the curve, and see if you can look at this equation and figure out why. Why is there symmetry? Okay, so there's two cases there basically to sketch, above the x-axis and below the x-axis. All right, so to get an understanding, I would look at what's happening not for particular values, but as x approaches those particular values. So what's happening as x approaches 0, y dash approaches 0. All right. You could do some other ones, for example, if you wanted to. You could look at, say, what happens as x and y approaches infinity. Or if that and that approach infinity, what's happening to the slope? Y dx will also be approaching infinity. You can see up here how steep it's getting. What happens as x approaches infinity? So if I said x approaches infinity and y approaches minus infinity, what would be happening to the derivative? The y dx would be approaching minus infinity, right? And that's that part of the curve there. So when you're doing your analysis to sketch your possible function, I'll be looking at the idea of limits, looking at what happens as x approaches particular values, right? Obviously, we know infinity is not a value, but you got the idea there. Now, if you want to try this on technology, here it is. Have a look. You can use GeoGebra, right? And all you got to do is type in this command, slope field bracket x squared y. And I just realised I've got that equation wrong. It should be slope field bracket 3x squared y. It'll give you a similar slope field anyway. But so yeah, that just here, that should be 3x squared y. I'll have to fix that up in my notes. All right, so make sure you've got all that down, all the way from all those annotations. Okay. Now, separation of variables. This is quite straightforward. And again, for those boys who are here for it, I'm going to do this in a little bit more detail so you'll pick up something. So, how do we solve? So we just sketched the slope field, but how do we solve the differential equation which is defined as f of x and g of y? Well, we can do it by separating variables, and that means we place the x and dx on one side and the y and dy on the other. Okay, so the other thing to think of is, the other thing to consider is this: what will that actually look like? Okay, well, when we separate them, you get the reciprocal of g of y on one side with the dy, and then f of x with the dx on the other side. Okay. Once you've done that, what do you do then? Well, you just stick an integral on both sides of the equation, and then you integrate both sides, and you try and make y the subject at the end if you can. Now, just be aware, not every differential equation is separable. Okay. And second is this to consider: why can you just whack an integral on both sides without considering the dx and dy? I'll show you why that can occur. Okay, so let's just say you had dy dx equals f of x g of y. Oops. G of y. Okay, so what I would be doing here is integrating both sides with respect to x. So what I'll be doing then is saying, okay, integral of dy dx with respect to x equals the integral f of x g of y dy. Okay, that's not right, is it? What you do to one side of the equation, you've got to do to the other, don't you? So technically, that should be a dx. That's what I want to show you. Okay, so these have to be the same because we're integrating both sides of the equation, which means we have to do it with respect to the same variable. Now, you can think of that and that as cancelling, okay? And you can think of the g of y on the right-hand side as independent of the x. So I can write this down now. Okay, integral dy equals, now I can think of this as, I can take this out kind of like a constant because it's not part of the integrating with respect to x. Okay. Then if I divide both sides by g of y, I'm going to get integral 1 on g of y dy equals the integral of f of x dx. So that's mathematically what's happening behind this step here. And it's just quicker to just put the integral signs in. That's essentially what you end up with. Okay, so let's have a look at first example here. Which of these are separable? Now let me just find out where my pen is. There it is. Okay, I'm going to try and use a different pen for this one so I won't get such wiggly lines. All right, so first of all, I'm just going to, if you like, cross multiply. So I'm going to get 5y cubed, 5y cubed dy equals 2x dx. Okay, now integrate both sides. Okay, so you just put the integral signs on both sides. Now, the question didn't say do the integration. It just said, can it be separated? And you can see I've separated the variables. I've got the y's on one side and the x's on the other, so that's all good. Copy that down. Now, what about the next one? Okay, so this is a little bit trickier. I've got, okay, so first of all, I'm going to put the minus sine x on the other side. And then obviously plus x, y. Now, having done that, there's not much you can do really, is there? You can't really separate the x out of that. Okay, so that is no, can't be separated. X and y cannot be separated. Okay, so let's go to the next one. This looks like we have more chance with this one. So now, here we go. All right, so let's just go x dy dx equals 2y. Okay, and then what we'll do there, I guess we could just go x dy equals 2y dx. And then if I take the reciprocals, what if I multiply both sides by essentially, okay, what do we do here? Okay, right, if I divide both sides by x, that'll work, and then both sides by 2y. So I should end up with 1 on 2y dy equals 1 on x dx, right? And then integral of that, integral of that, I've done it. So, yep, both of those, the variables can be separated. That's true. Okay, no problems there. All right, what about this equation here? Solving dy dx equals 3x squared y. All right, so let's see how we're going to do that. All right, firstly, now here's my pen, here we go. All right, so I'm going to hold this pen, right? All right, so what are we going to do here? We're going to solve this. So we're going to separate the variables. Let's see how we do that. So we'll start off with dy equals 3x squared y dx. Okay, right into Benita here, that's good. And then divide by y, you're going to get 1 on y dy equals 3x squared. I'm getting the hang of this pen. Now, integrate both sides. Yep. Now, that's going to be log of mod y equals, it'll be x cubed plus c. Now, raise both sides to e. So you're going to have e to the log, e to the log, no, this pen is malfunctioning, very sensitive. I have to go back to my pen. Yeah. Too many buttons on this. Okay. Now where am I? Here we go. Let's try that again. E to the log of mod y equals e to the x cubed plus c. Okay. Now that's going to give you mod y equals. Now think of this as e to the x cubed. Oh, come on. E to the x cubed times e to the c. Okay. That's going to give you mod y equals, now e to the c is just a constant, so I could write this as a e to the x cubed. Okay. So that is essentially your answer. Now, we should give this a little bit of extra information. So if I just scroll down here. All right, so what can I say then? about this equation? Well, essentially, you've got to consider the plus and minus cases, don't you? So you're going to say y will be equal to a e to the x cubed, right? If y is bigger than 0. And by the way, I should make a qualification over here that a is definitely positive. Why is a positive? Is because e to the c, whoops, missed that one, e to the c is positive. Now, what else could I say? I could say that y equals minus a e to the x cubed if y is less than 0. So that's the negative case. All right. Now, how does that look? Hey presto, I've already drawn the graph for you down here. So you can see here y bigger than 0 and y less than 0. There's two cases. Now just be aware though, down here, it looks like it's on the x-axis. It isn't. It's approaching. Okay, it's approaching. Because if you think about it, if I have, let's consider the case above the x-axis, e to the x cubed. All right. Now, the case, what can I say about the y values here? Well, the y values are always positive, aren't they? They are always positive. Okay, so above the x-axis, that curve will always be, right? Even though on the diagram it looks like it touches, that's because we haven't zoomed in enough. If you zoom into that function enough, you'll find that it never touches the x-axis. Okay, so you can see here, the y values of this function can never be 0, can they? All right. So let's have a look at the next one. All right, so for this one here, this is exactly the same question, but they tell you two conditions. There's a 0.01 on the original function and y can't be 0. So what I'm going to tell you is this, rather than doing all the working out from scratch, let's just say mod y is equal to a e to the x cubed. All right, now it tells me that when x is 0, y is 1, so I'm just going to go 1 is equal to, now I could do modulus of 1, but it's just 1. 1 is equal to a e to the 0. All right, so that means 1 is equal to a, and that means my equation is mod y equals 1 e to the x cubed, e to the x cubed. There we go. All right, so now, by the way, something to be aware of, I'll just draw a line here. What happens is I've got a positive and negative case. Okay, so it means y equals e to the x cubed for y bigger than 0, and y equals minus e to the x cubed for y less than 0. Now, if that's twisting your brain up, think about it like this. Remember, with absolute value, you've got a plus or minus case. So you could just think of this as plus or minus. Okay, just think about it like that if that's the easiest. All right. But just be aware that I think it's important to think of it in terms of the absolute value definition, because this tells you above the x-axis I have e to the x cubed, and whoops, I made a mistake there, didn't I? Just realised that. Glad I picked it up. Click on the eraser. No. Click on the eraser here, and that should not be a greater than sign, should it be? It should be a less than sign. Okay, alrighty. Now, what does that look like? Fairly similar to the last one. Notice it goes through, you've got a stationary point at y equals 1 and negative 1, whereas in the previous one, it was a bit higher, right? Now, by the way, in the previous example, there was no way of knowing if this is the particular function because we don't know what a is. This is one possible answer. Okay. That's basically what it looks like. All right, so just remember, how did I get those absolute values things sorted out? Remember, I had the definition. Whoops, wrong there. Absolute value of x equals x for x bigger equal to 0, and it's equal to minus x for, okay. So that's where I got the greater than or less than symbols over here, there, and there. So I did it from the absolute value definition. And I know some of you will be saying, yes, but you didn't do equal to 0. Yes, that's true. But if you look at the question, right, the question said, y not equal to 0. All right, did say that. All right, let's scroll down. And we're looking at, oops, I don't know why there's a blank page there. Have to fix it up. And let's do these questions. All right. So find the general solution of f dash of x equals x squared y. All right, so I'm going to switch to the other pen for this to make it faster. All right, so let's have a look. So I'm going to have a wonky writing. Part A, you've got dy dx equals x squared on y. Okay, so let's just cross multiply. So you're going to get y dy equals x squared dx. Okay, and then integral signs there. And then you're going to get y squared on 2 equals x cubed on 3 plus c. Now I could have done a plus c on the left-hand side. Doesn't matter. You just need one constant, that's all. Okay. All right, next part of the question is we're going to then go, well, y squared is equal to, multiply both sides by 2, plus 2c, and yes, I could replace this whole thing with a different constant, but I'm not going to, and then plus or minus the square root of 2x cubed on 3 plus 2c. Okay, so that's your solution. That's the general solution. General solution, okay? Now, why is it a general solution? Well, it's because there's a c there, there's a constant. Generates simple in many cases. Okay, now it says in part B, so let's just scroll up. Part B, find the solution given that f of 3 equals -2. Let's just scroll up here. And f of 3 equals -2. So for part B, let's just change colours. Give it more interesting to look at. So it tells me that x equals 3, and it tells me that y equals -2. All right, now, what am I going to do? I'm going to actually sub that into this equation. Sub into y squared equals 2/3 x cubed. No, actually, I won't do that one. I'll tell a lie. So I just want to find out what c is. So I think the best equation to use to find out what c is this one. I'm going to use this equation. Y squared on 2 equals x cubed on 3 plus c. It doesn't matter which equation you use, but I just think this is easier. Sub it into that one. And, okay, so put a -2, you're going to get 4 on 2 equals 27 on 3 plus c. So that's 2 is equal to 9 plus c. So that gives you c equals -7. Okay. Right, coming over here. So what's that going to give us? We sub it in, sub in c. You're going to get y equals plus or minus the square root of 2x cubed on 3 minus 14. Okay, that's your final answer. Now, just a word of advice on the previous question I just remembered. Okay. Previous question. Here, have a look. Now, I disagree to the answer in the back of the book. Okay. If you look, it's not the back of the book. If you look at the textbook, they just take the positive case, but they are wrong. Okay. You cannot just eliminate the absolute value. You've got to take that into consideration. So I disagree with the textbook on this one, right? So you've got to be consistent mathematically, and they haven't been consistent mathematically in that. So you need the plus and minus cases, right? So, all right, that covers all the examples. So what do I want you to do then for homework? For homework, you now have all the knowledge to do 1303 from the textbook, and you can do all the questions 1 to 8. All right. Thanks for listening. I'm still figuring this technology out. This virtual pen is a bit of a pain. It requires a lot of concentration for me not to press the wrong buttons on the pen. But I'm sure I'll get faster the more I do this. So I hope you enjoyed the lesson. And make sure you keep up your exercise, get enough sleep. We're in a bit of a stressful situation at the moment, but I've figured out now how to get you quality lessons. Okay, so I'm just going to stop sharing and see you next lesson.